This is a quick video to visualize the effect of noise in digital transmission. Here we've got a digital data sequence and we're showing the case for binary phase shift keying. This is the transmitted modulated waveform. So here when a 0 is being transmitted, we're transmitting it with a cos wave, and when a 1 is transmitted, we are using a negative cos wave. At the receiver, we're showing that signal here. The signal is going to have a lower amplitude because there's attenuation. In this case, we're showing a channel with 10 dB loss. And there's also going to be noise in the receiver. In this case, I'm showing it for a signal to noise ratio of 100 dB. That's a very high signal in comparison to the noise. So you're almost seeing, of course, no noise here. Another way of visualizing this transmission is with a constellation diagram. And here we are showing on the x-axis, the in-phase component, so that's a cos wave, and on the vertical axis, the quadrature component, that's a sine wave. And in this waveform here, there's no sine wave component, only cos, and you can hopefully just make out this small yellow dot here at 1, which represents a cos wave, and a small yellow dot here at -1, which represents the negative cos wave. So for each one of these symbol periods, it can be represented by a dot on this constellation diagram. When there's no noise, there will either be a dot at +1 here or -1 here. So let's see the effect of adding noise, so a more noisy receiver electronics. And here's the case when the SNR equals 10 dB. Of course, the top two figures are the same. Now at the receiver, there's more effect from noise, and you can see that the signal is no longer a nice clean cos wave. And the detector's challenge is to take this waveform and try to decide whether it was a cos wave or a negative cos wave. And I think you can see for 10 dB SNR, it probably isn't too hard to achieve that. And if we look at the constellation diagram, we can see now the dots are no longer at +1 and -1. They are scattered around due to the noise in this waveform. Each one of these yellow dots represents the output of the demodulator for the corresponding period of the received waveform. The demodulator takes this waveform and tries to work out the amplitude and phase of the sinusoidal waveform that it's receiving. Because of noise, it's not going to be exactly at +1 or -1. It's scattered around. The job of the detector is to take the output from the demodulator and decide whether it represents a 1 or a 0. This can be done by seeing which side of this boundary, in this binary case, which side of this vertical line the dots lie. And for this signal to noise ratio of 10 dB, they're all clustered and no errors have been made. You can clearly see there's 5 dots on the right-hand side here. That means there's 5 cos waves. This is the positive one, which is the cos waves. That corresponds to this waveform here, which corresponds to the zeros. And if we look at our waveform, then yes, we have 5 zeros in our sequence. So that matches up. Let's look at it for an even lower signal to noise ratio. Here's an example when the signal to noise ratio is 1 dB. There's a lot more noise. And clearly it's going to be very challenging for the demodulator to get the correct amplitude and phase based on receiving this signal. And when we look at the constellation diagram, we can see that errors have been made. In this case, there's only 3 yellow dots on the left-hand side of this axis. There's so much uncertainty from this signal that we've now got dots appearing on the wrong side of the axis. And this effect is only going to be worse when we have higher order constellations. And here's an example of 16 QAM. In this case, there are 16 different possible amplitude and phase combinations, and they're indexed by the data. So there's 16 possible data values. And you can see here in the modulated waveform, there are 3 different amplitude levels, and there's lots of different phases. Here I'm showing the case when the SNR is 30 decibels. And here is the constellation diagram in this case, showing the 16 different combinations of amplitudes and phase. When it is 30 decibels, all of the outputs of the demodulator are closely compact around their actual values. And the detector would have no trouble in detecting between these by simply having the boundaries between each of these possible constellation points. Let's look at the effect when the noise is increased, or in other words, the signal-to-noise ratio is decreased. And here's what the received waveform looks like when the SNR is 10 dB. There's still clearly a sinusoidal component there, and visually by looking at this, we should think probably it's not going to be too hard to tell between the different amplitudes and phases. However, looking at the constellation diagram, we can clearly see that this is not going to be the case. Even though visually we might think that this still looks like the nice sinusoids, when it comes to the output of the demodulator, there is a large spreading out in those constellation points. And it's going to be a case that there are going to be lots of errors at 10 dB for QAM. So if you remember for BPSK, we were able to go down close to 1 dB, but for QAM, it's going to be very challenging even at 10 dB. So hopefully these waveforms have given you more insights into visualizing the effect of noise in digital detection. If it has, give the video a like. It helps others to find the video. Of course, subscribe to the channel for more videos and check out the description below. You'll find a web page that has a full categorized listing of all the videos on the channel.